Today we are going to be talking about mesh analysis. This is going to be very similar to nodal analysis in as much as it is an algorithm that we're going to follow. I have a University Senate meeting at 4, which means I need to leave here at about 3:50. So you guys are going to get out roughly half an hour earlier. The tutoring session will be open from 4:30 to 5:30 p.m. Neskin Hall, room 105. The Eta Kappa Nu, so the Engineering Honor Society students will be there covering for me today, because like I said, I have that University Senate meeting. So, if nodal analysis was solving circuits using multiple applications of Kirchhoff's current law, mesh analysis is simply solving circuits for all of their currents using multiple applications of Kirchhoff's voltage law, okay? So there's a similar order of steps and all that kind of good stuff. So let's start with the following problem. Let's say that we have an 8-volt source. Then we have a 5 ohm resistor. A 3 VX source like so. A 9 ohm resistor. 12 ohm resistor. And the 2-volt source over here. And I'm going to define Vx to be actually, that's too easy. The voltage drop over the 9 ohm resistor positive polarity terminal on the left. Okay. So the first thing that we are going to do when applying the mesh analysis technique is to identify our meshes. So who of you can remember from literally the very first class meeting that we had what a mesh is? Exactly right. A loop that doesn't contain any smaller loops. So I could consider this loop a mesh, this loop a mesh, and this loop a mesh. My second step will be to assign mesh currents. So I might call this guy mesh current A, this guy mesh current B, and this guy mesh current C. Okay. So these mesh currents, I choose to draw them as flowing around their mesh in a clockwise direction. All right. There is nothing remotely wrong with you choosing a counterclockwise direction for all of them. There's technically nothing wrong with you mixing and matching clockwise and counterclockwise, clockwise and counterclockwise directions. However, I would argue that if you mix things up, it's really hard to kind of figure out what's going on, because some places you'll expect negative voltages and wind up with positive and all that kind of good stuff. So I would argue use all clockwise or all counterclockwise to eliminate as many ambiguities as possible. All right. So this particular problem contains a dependent source intentionally. So my next step is going to be express controlling variables in terms of mesh currents. All right. So our controlling variable in this case is that voltage Vx, right? Because it's what's controlling the output of that dependent voltage source. So how do you guys think we are going to express that voltage Vx in terms of our mesh currents? Any thoughts? Pardon? Current IB times 9 ohms. Anybody else? I do. Seems perfectly reasonable, right? V is equal to I times R. So the voltage drop across the 9 ohm resistor with the positive polarity terminal on the left should just be IB multiplied by 9 ohms. So in this case, I'm going to write Vx is equal IB times 9 ohms. Now, what if I had given the voltage drop with a positive polarity on the right? Negative IB, right? Because we have a negative current of IB flowing into the positive polarity terminal. Okay. So nothing wild or crazy there. All right. You guys are all catching on to this. Fantastic. Step number 4 will be apply Kirchhoff's voltage law around all meshes. So I apply KVL at mesh A. I'm going to start here, this bottom left-hand corner, and just apply Kirchhoff's voltage law around this loop. So what's really interesting about mesh currents is they're not like branch currents because they're not necessarily a current confined to a single element. It's a current or some portion of flowing through all of those elements. All right. So if I start at the bottom left-hand corner, what's the first thing I see? Negative 8 volts, because I see the negative polarity terminal first, right? Negative 8 volts. Then I see the 5 ohm resistor. And so effectively what I'm going to be doing here is I'm assuming that the current is flowing into the positive polarity terminal, okay? So I'm going to express this voltage drop as 5 times IA. Then I see my negative polarity terminal for my dependent source. So I'm going to call that negative 3 Vx. And I'm going to go ahead and make that substitution, right? Or I can say that Vx is 9 ohms multiplied by IB, just so I don't have to do it in an entirely separate step. And I set these guys equal to 0 because I've started off at the node, or excuse me, I've left off at the node that I started at. Ian.
Basically, would you say that like the different, if you were looking at it not in terms of meshes, but with the mesh numbers, like the current 3dx is IB minus IA?
Yes, we'll get to that in just a moment. Yeah, you're absolutely correct. So when we, I see where your mind is going, and we will.
Like what the mesh currents are relative to like a bigger current.
Yeah, absolutely. So let's look at mesh B. All right, so I'm going to start here. Obviously, I see at the positive polarity terminal of my dependent source first. So I'm going to have positive 3 times 9 ohms times IB. So that's my 3Vx. Then I see 9 ohms times IB. And we're about to get what Ian was just talking about here. The next thing we see is a 12 ohm resistor. Okay. The 12 ohm resistor has two mesh currents flowing through it, right? As mesh current B goes around its clockwise path through the 12 ohm resistor, it is going down. And mesh current C through the 12 ohm resistor is going up. So what we'll find is that the total current flowing through that 12 ohm resistor as we follow IB around its clockwise path is IB minus IC, because IC is in the opposite direction. Yes, so we're assuming that the current that we're following around is flowing into the positive polarity terminal. Since IC is in the opposite direction of our current IB that we're following around, that's why it gets the negative sign.
So when we do mesh C, it's going to be IC.
Exactly right. So as we start mesh C, the first thing we see is that same 12 ohm resistor. But now, since we're following IC around its clockwise path, it's going to get the positive sign. IB is flowing in the opposite direction, so it gets the negative sign. And so we get 12, oh, excuse me, this guy was set to 0. 12 ohms IC minus IB plus 12 volts is equal to 0. Sorry, 2 volts, thank you. Erase. We now have 3 equations with 3 unknowns, so we could solve for all 3 of those mesh currents. Ginny, what's up? So your question was if Vx, oh, let me get closer so I can hear you better. Well, 3Vx will never be a resistor. Like if there, okay, so if there are a resistor there, okay, so if that wasn't the voltage source, absolutely. So if the 3Vx dependent source here were a resistor instead, then it would have been resistor value times IA minus IB in our mesh A equation, and it would have been resistor IB minus IC in our mesh B equation. Absolutely correct. So the reason why we didn't have to put things in terms of a mesh current is because we had a voltage source, right? Kirchhoff's voltage law is us simply adding up voltage drops, and the voltage drop is well defined, and actually has no relation whatsoever to the mesh current other than through Vx. Yes.
Since we're only looking for current B and mesh B and C don't use IA, can we do it as a 2 variable system equation? Just ignore mesh A equation.
So you are saying mesh B, excuse me, our KVL equation for mesh B and our KVL equation for mesh C do not have any dependence on mesh current A whatsoever. So yeah, we technically could solve those 2 as a system and then use the result of that to solve for mesh current A. Yeah, in this particular instance, the way I've drawn it, absolutely, yeah. But I would argue that if your calculator can solve a 2x2 system, it can also solve a 3x3 system. So why not do it in one go? Just saying. All right. So let's take a moment and solve for these three mesh currents. So my coefficient for IA in my first equation is 5. My coefficient for IB in my first equation is -27. My coefficient for IC in my first equation is 0. My constant value is 8. In my second equation, my coefficient for IA is 0. My coefficient for IB is 27 plus 9 plus 12. My coefficient for IC is -12. Constant value is 0. I am using a TI 36. That's the one that I'm most familiar with. Then let's see, for my mesh C equation, I have 0 IA, -12 IB, +12 IC, -2 volts when I move it over. When I solve, I get IA to be 1.986, IB to be 0.071 amps, and IC to be -0.095. Everybody get something different. Always a possibility I type something into my calculator incorrectly. What did you get?
For IB, I got -0.0555 amps, and for negative IC, -0.222.
All right, so let me see here. System. All right. So 3 times 9 is totally 27, so that checks out. All right. So let's see. 27 plus 9 plus 12. Oh yeah, so for whatever reason here on IC, I have 36 and it should be -12. So I don't know where the heck that came from. That is correct. The coefficient for IA in the first equation is 5. The coefficient for IB is -27. Coefficient for IC is 0, and then it is equal to 8. Let me hit solve here. I think that fixed it. So, all right, let me erase these incorrect answers. I got 1.3 amps here, -0.5 repeating here. Excuse me, is 0.5. Right, pen thingy. And then -0.2 repeating. Apologize for my mistake. So largely, mesh isn't particularly different than nodal analysis at all, right? We worked this one with a couple of independent voltage sources and one dependent source. I intentionally avoided current sources, so now let's throw a current source into the mix and break stuff. So let's see what I can do. All right, so this circuit that I've drawn here, let me just throw some arbitrary values in: 12 volts, 7 volts, 11 ohms, 8 ohms, 3 ohms, 4 ohms, 2 amps, twice Vx, where let's make this difficult. Here's our voltage Vx, right? I can define a voltage as the potential difference between any 2 points in a circuit. So those are the 2 points over which I've defined that voltage Vx. So we have 3 meshes because we have 3 window panes. So this is going to be fairly nice and easy on that end. Let's call this mesh IA, this upper mesh IB, and this mesh IC. So because we have a dependent source that has a controlling variable Vx, I would argue that we need to determine what that controlling variable Vx is in terms of our mesh currents. Anybody have any thoughts on how we might approach this? Yeah, so if we're trying to express it in terms of the mesh current, so utilizing things like IB, IC, IA, and all that kind of stuff is absolutely fair game.
Yeah, so then we would, the voltage drop, since it's within the mesh, we could go through the volt and source, or we could just go through the 2 resistors, I think, right? To the loop voltage is 0.
Okay, so you are saying
Current through the 2 resistors times the 2 resistors.
okay, so I'm going to call this guy right here positive polarity on top, negative polarity on bottom, V8, like so. And I'm going to call this guy right here positive polarity on the left, negative polarity on the right, V3. We could see, I hope very easily, using Kirchhoff's voltage law, that Vx is simply going to be V8 plus V3. Anybody have a problem with that? V8 plus V3. Yeah, so we're kind of cutting across the diagonal of that top right box. So let's say that we started in the bottom left-hand corner. We would see negative V8 plus Vx minus V3 is equal to 0. And with a little moving things around, that gives us Vx is equal to V8 plus V3. Right. So I'm doing Kirchhoff's voltage law around that path that cuts through the diagonal because I'm trying to find that voltage drop across that diagonal thing. Ian.
We would never do this, but technically, it's like for the sake of it. Would you do like the voltage drop across the 8 ohm, the 11 ohm, the 7 volt source, and the 4 ohm to get it? Like, would that give you the right answer if you would do that?
It's 11, 7. Yes. You could write any KVL loop that you wanted to.
Yeah, that's like the big one for the circuit.
Yeah, so you could absolutely do that, but why? Yeah.
I was making sure that's like how it works.
Yeah, well, it's Kirchhoff's voltage law. It works how Kirchhoff's voltage law works. Kirchhoff's voltage law is path independent. As long as you start and end at the same point, doesn't matter what circuitous route you go through. All right, so another suggestion, and we'll do the math on this part in just a moment, but another suggestion that Ian had was we could say it's the voltage drop over the 12 volt source and then the voltage drop over that dependent current source, right? So let me talk to you about why you wouldn't want to use that particular route, which is going to introduce the concept of super meshes in a moment. When we have a current source, it has a fixed amount of current regardless of the voltage drop over it. In fact, there is no relationship between the current that's being provided by the source and the voltage drop over it, right? So we're going to run into a very, very similar issue when we try to express the current flowing through a voltage source in nodal analysis, as we will have here when we're trying to express the voltage drop over a current source. They are so unrelated, we have to avoid them in some way, shape, or form. In nodal analysis, we avoided them by creating a super node where that same current, that voltage source current was exiting and entering the node simultaneously so that they canceled each other out, right? We're going to wind up doing a similar thing here. So let's circle back around. I want to express Vx. As I said, it should be V8 plus V3. Well, how do I express that voltage V8 in terms of my mesh currents? Eight times IB. So the problem with that is that mesh current IB is flowing into the negative polarity terminal. So it should be negative 8 times IB. Now, how do I express that voltage V3 in terms of my mesh currents? So negative 3 times IB minus IC, okay, or positive 3 IC minus IB. Either way works for me. I personally try to avoid having an excess of negative signs.
Right now we're doing Hartman's voltage law across the top right now.
Sure. Yeah, across the top mesh, yeah. Going around that left triangular path. Well, so that's what I did to get that Vx is equal to V8 plus V3. I mean, if let me move this down a smidge, because I have enough practice to be able to do it in my head, but potentially there might be some confusion here. So when I started in the bottom left-hand corner, I had negative V8 plus Vx minus V3 is equal to 0. I started at the bottom left-hand corner, saw the negative polarity terminal of my voltage drop V8 first, positive polarity terminal of my voltage drop Vx, then the negative polarity terminal of my voltage drop V3. If I move V8 and V3 to the other side of the equal sign, I get that next expression. Once you can do this enough, you can easily see that the voltage drop is going to, the voltage rise will be equal to the sum of the voltage drops, or however you want to express it, but you'll get used to doing the polarities and crap like that in your head. Then, based on the expression Vx is equal to V8 plus V3, I wanted to figure out how to express that voltage V8 and that voltage V3 in terms of those mesh currents, right? So we said that V8 was equal to negative IB times 8 ohms, because the current IB, as it flows around its clockwise path, enters the negative polarity terminal of that voltage V8. And then V3, oh, and there is no opposing mesh current because it's on the outside edge of the circuit, right? For that current I3, or excuse me, for that resistor 3 ohms there, because it's inside on the interior of the circuit, it will have 2 contributions from the mesh currents, right? The current IC flows into the positive polarity terminal, and the current IB flows into the negative polarity terminal, which is which is why we have 3 ohms times IC minus IB.
So if it was going into the positive terminal of the IC plus IB,
That if it were flowing,
or it'd be negative IC plus IB.
right. So if I flipped the polarity of that voltage V3, then IB would be flowing into the positive polarity terminal and IC would be flowing into the negative polarity terminal. I chose those polarities to make my Kirchhoff's voltage law equation at the top work out to be my variable Vx is equal to the sum of those voltage drops. It doesn't particularly, I can mess up those guesses as to my polarities for my resistors, no problem whatsoever, as long as I'm applying Ohm's law correctly when I write my last expression. So that's just me having enough practice to set it up in that way. All right, so we have gotten our dependence equation. Now let's attempt to write a Kirchhoff's current law expression for mesh A. Excuse me, Kirchhoff's voltage law. Well, can't give me credit for it. A dude made it up about 100+ years before I was born. All right, so for mesh A, starting at the bottom left-hand corner, I would have -7 volts plus 11 ohms times IA, and then I get to that little pickle that we talked about a moment ago. And I am trying to express the voltage drop over my current source in terms of my mesh currents, and there is no relationship between those two quantities. The absolute best I can do is call this, and I'm just taking a wild stab in the dark here, VCS, assuming positive polarity on top. And when I write my KVL equation for mesh B, I would now see the negative polarity terminal. So I'd have negative VCS plus, actually I'm doing mesh C, thank you, I'm sorry. Thank you, my head's up my butt today. Mesh C, yeah, so I'd have negative VCS plus 3 ohms, IC minus IB plus 4 ohms times IC is equal to 0. All right. So I'm going to do exactly what I did on Friday. I'm going to apply mesh analysis or Kirchhoff's voltage law to the combination of these two meshes. Okay, so what I'm doing is I'm following this path that I've outlined in purple, because that allows me to avoid having to try to express what the voltage drop is over a current source in terms of mesh current, right? I'm avoiding that entirely. So KCL, excuse me, KVL, goodness gracious, at super mesh AC is just KVL at mesh A plus KVL at mesh C. I literally add those two things together, and that voltage drop winds up canceling itself out because I see it from the positive polarity perspective first, and then I see it from the negative polarity perspective when I go the other way around. And what I get is -7 volts plus 11 ohms, goodness, IA plus 3 ohms, IC minus IB plus 4 ohms, IC is equal to 0. So I combined these guys effectively into this one equation, all right? I'm going to have to do an operation like that for every interior current source that I have, okay? So what I mean by an interior current source is it's one that doesn't show up on the edge of the circuit, all right? I have a conundrum still though, in as much as I am using two meshes, so I expect to get two equations out of it. Where's my second equation going to come from? Any thoughts? So when we had a voltage source in nodal analysis, we wound up having a voltage relationship equation. So in mesh analysis, when we have current sources, we should have a current relationship equation, right? Every current source will yield a current relationship equation. So, Destiny, I'm going to pick on you because I didn't pick on you the other day. What do you feel like the current relationship equation should be for that 2 amp source in the middle? Any thoughts? What are the two meshes that are touching? What are the two mesh currents that flow through that 2 amp source? IA and IC, absolutely right. Which of those two mesh currents flows in the same direction as the 2 amp source? Okay, and then IA flows in the opposite direction. So what we'll see is that 2 amps will be equal to IC minus IA. So the current flowing in the same direction as the current source gets the positive sign. The current flowing in the opposite direction of the current source gets the minus sign.
Why can't you just say opposite?
That's not true. Where's that relationship coming from?
That same wire, so I thought.
Right, but so IC and IA are opposite each other through that branch in the middle that contains the 2 amp current source. They don't necessarily have the same magnitude. In fact, I would argue that they can't, because if they had the same magnitude, we would have a 0 amp current source in the middle, right? So that current source is forcing 2 amps to flow up. And we know that the difference between those two currents, those two mesh currents, then has to be 2 amps. All right. So our current relationship equation here will be IC minus IA is equal to 2 amperes. Now let's take a look at mesh B. Mesh B contains a current source, but it is on the perimeter of the circuit. Okay. So what we did when we had a current source on the interior of the circuit was we tried to write a path for us to apply KVL around that avoided that interior current source. But when we have a current source on the edge, it is literally impossible to write a path that avoids that current source. So whenever we have a current source on the edge of a circuit, we are just going to have a current relationship equation. There is no way for us to apply KVL. So this is the similar situation to when we had a voltage. Whoever's turned their sound on, okay. A voltage source at a supernode that contained ground, right? This is a very similar situation, okay? So we have a current source here, 2Vx. Write this down here. How does that current source 2Vx relate to our mesh currents? Just equal to IB, full stop, no extra work. Oops. Okay. So let's look at the 2Vx source, all right? By definition, from that source, there is a current that is flowing down that has a voltage, or excuse me, has a current of 2Vx, right? Because it's a current source. As we follow IB around its clockwise path, so it starts here, goes up, flows through the 8 ohm resistor, turns this corner, flows into the positive polarity terminal of the 12-volt source, turns this corner, and it is now flowing in the same direction as that current 2Vx. And it is the only mesh current that's flowing through that current source because the current source is on the edge of the circuit. So there's no opposing current that could cancel any portion of it out. So that's why IB, right? So this is representative of IB. This guy right here is representative of IB. This guy right here is IB. So IB and 2Vx represent the exact same current. Does that make sense? Okay. So it's similar to a homework problem. I think you guys had it was a single node pair problem where you had a current IZ direction down and a current source that was like 0.25 Vx direction up, and you had to write an equation, and it wound up being IZ is equal to negative that. It's because they were representing the same current through the same branch, but in equal and opposite directions. Well, here you have the same current flowing through the same branch, but they're flowing in the same direction, so you don't have to deal with the negative sign. Okay. So now we have enough information substituting in that relationship for Vx into our equation down here to where we could solve this system. And I'm going to be lazy and not do it because I don't want to make another dumb mistake in front of you guys. Ian.
So regardless of like dependence or independence, if we have like multiple alternatives, that's enough.
No. So let me, that's a good question. Current sources on the perimeter, so current sources in parallel combine, right? So
Oh, they'd be equal. You wouldn't have two independent current sources of different values within the same mesh on the perimeter.
correct, you
It's
can't.
not gonna be possible.
Yeah, that violates the rules. Yeah. So I want to pass out the in-class assignment sheet, and we're going to work problem 3 together, actually, because this is interesting to me. Because it throws a little bit of a monkey wrench into things here. There's nothing that we haven't covered in the lecture. We're going to start with the first problem, and then we'll you guys to do the first 2 problems. All right. Thank you. I'm going to take a minute to write this problem down. So this will be ICA 7.3. All right, so we have our 5 ohm resistor, our 20 ohm resistor, our 16 ohm resistor up here, 25 ohm resistor down here, 21 ohm resistor. This is a 0.5 Vx source, where Vx is defined to be the voltage between these 2 points in the circuit. All right, so what's the first thing that I should do? Identify my meshes, all right? Now I'm going to label them. So let's call this guy IA, this guy IB, and this guy IC. I'm about to start getting an error over and over again, so I'm going to save this, close it, and restart it. Yes, I'm a dork. All right, video games aside, we have done steps 1 and 2. All right. This voltage Vx, this is another one. I like to do things like this on your exams where I choose a controlling voltage that is ostensibly difficult to express, okay? So somebody tell me what to do for this particular one. How am I going to express that voltage Vx in terms of my mesh currents? You're pretty close, all right? There's 2 different paths that we could take here. We could either go around the top right triangle or the bottom, so the top right triangle in that top left mesh, or the bottom right triangle in that same top left mesh, right? So if we go around the top right triangle, it's going to be practically identical to what we did in the last example problem. But if we go around the bottom left triangle, it's going to be a little bit easier because there's only one resistor there, right? So effectively, Vx, even though it's drawn all weird and stuff, intentionally by me, because I can be a bit of a jerk, it really is just the voltage drop over that 21 ohm resistor, positive polarity terminal on the right, negative polarity terminal on the left. Everybody see that? Okay. So be on the lookout for me being a salty jackass on your exams, because I will do stuff like that all day long. All right, so let's get back to what Cheston said. I believe he said it was Vx is equal to 21 IA. There's a small problem with that. Anybody know what it is?
16 ohm IA and IB. You can't just add them up.
So what's the 16 ohm resistor got to do with the 21 ohm resistor? So that's the one we're talking about.
I'm sorry, I was thinking you were adding up 5 ohms.
No.
So 21 ohm deals with IA and IC.
Exactly right. That mesh current of IC is flowing into the negative polarity terminal, so we have to take that into account. So whenever we have an element that is on the interior of the circuit, there's always going to be some opposing current, mesh current, that we need to take into account as well. It's a very easy and common mistake to make, which is why I'm trying to hammer this into you guys' heads. So our correct expression for determining Vx should be 21 ohms, and then IA is flowing into the positive polarity terminal, and IC is flowing into the negative polarity terminal. So it's IA minus IC. All right. Now, since we have 2 current sources, let's go ahead and write our current relationship equations as well before we forget about it. Alexis, what should my current relationship equation be for my dependent source, that 0.5 Vx current source there in the middle of the circuit? Yeah, so effectively, which current's flowing in the same direction minus the current, the mesh current flowing in the same direction as the current source, minus the mesh current flowing in the opposite direction as the current source. IC minus IB. Absolutely correct. We have our other current source. Anita, I've unfortunately learned your name. How do I express that 7 amp current source in terms of our mesh currents? So it's on the edge, right? Whenever we have a current source on the edge of a circuit, it's only going to be related to a single mesh current. Seven amps, okay. All right. Caitlin, you got a thought? You're shaking your head no. Eli. That's absolutely correct. 7 amps is equal, IC, right? The only mesh current that's flowing through that bottom branch is that mesh current IC as it goes around its clockwise path. And it's flowing in the same direction as the 7 amp source. So IC has to be equal to 7 amps.
Where did we have VX equalize?
So that comes from this current source right here. Right? It's a current source because there's an arrow. The current IC is flowing in the same direction as the current source. Current IB is flowing in the opposite direction, which is why we get 0.5 Vx, the current being supplied by the source, is equal to IC, the current flowing in the same direction, minus IB, the current flowing in the opposite direction. We effectively did the exact same thing for the 7 amp source, except that there's no current flowing in the opposite direction because it's on the edge.
Why are you able to just ignore all the other?
Because they're all connected in series to it, and current flowing through all of those elements in series doesn't matter, right? We're dealing only with mesh currents here, and we're trying to develop current relationships. These are not KVL equations, okay? These are current relationship equations. So only currents that show up in. All right. So we have an interesting thing here, okay? We have an interior current source, that dependent source. So ostensibly, we should be trying to find a path that encloses that interior current source so that we can avoid writing a Kirchhoff's voltage law relationship over it. But it should be fairly obvious that there's no way for us to do that. And the reason for that is because the super mesh, right? So let's say that we were trying to write a super mesh thing like we did before. Okay, so let me scroll up to the previous page so that we can kind of review what I did. All right. So I said there is a current source between mesh A and mesh C. So I'm going to create a path around it so that I don't have to take the voltage drop over that current source, right? If we look at this problem, there is a current source between mesh B and mesh C. The problem here is that mesh C has a current source on the perimeter, which means I literally cannot write a Kirchhoff's voltage law equation for that super mesh. I don't need it. I don't need it at all. If you notice here, including Vx, we have 4 unknowns, right? IA, IB, IC, and Vx. We have 3 equations. We have not even looked at mesh A at all yet. That's where our 4th equation is going to come from. So what I am trying to get at here is that if you have super meshes that contain a current source on the perimeter, you'll never wind up writing a KVL equation for any of those meshes involved. Okay, you'll only deal with current relationships. So if there were a current source anywhere on mesh A, we couldn't do any Kirchhoff's voltage law for this entire problem. It would literally just be current relationships, and then we'd solve that system of current relationships to figure out what was going on. Okay. So how am I going to write my Kirchhoff's voltage law equation for mesh A? IA times 5 ohms. All right. So the current, so we are assuming for every resistor we see that as we're following mesh current IA around its clockwise path, it is flowing into the positive polarity terminal of all of our resistors. So 5 ohms times IA, what comes next? All right, 16 ohms, IA minus IB. What's next? Set it equal to 0, and we can now solve for everything. All right, we can substitute our Vx relationship at the top into our second equation, leaving us 3 equations, 3 unknowns, and we're good to go. Everything past that is just simple. I say simple to me manipulation. All right. So we have an expression for Vx, so it should be fairly straightforward to figure out what the answer for the first part is, and then the power supplied by each of the sources would require us to write Kirchhoff's voltage law equations once we know what those currents are, so that we can express all the voltage drops over the resistors as a finite value and then figure out what the voltage drops over the current is.